Good evening. This talk is going to be about concurrency, and I will be focusing on a specific model of concurrency called the ACTOR model. There are several models, but this is the one that sort of has most of my interest nowadays. Speaking of me, I work at IMG Gaming. It's a division under a much larger company called IMG. And what we do is basically handle data from sporting events and that sort of thing. So we handle data from ATP, UFC, badminton, EuroLeague, and basketball and that sort of thing. What that means is that we have to work with data really quickly and in very unpredictable ways. And so that's basically my focus nowadays. And in my spare time, I'm working on a PhD, which also has to do with the ACTOR model. So yeah, you can tell I'm all up in here in this sort of thing. And I previously worked with our gracious hosts, and they will tell you that in as much as I enjoyed working with them, my heart sort of lay elsewhere. And so I kind of sort of left them and went into this. So without further ado, let's talk about concurrency, shall we? What is concurrency? It's the task of writing a program with multiple threads of control. What that means is that we need to control the way our programs generally flow, but the problem we get is that we always think sequentially. We always think about things moving in a straight line, when in real life, it's not. I'll give you an example. When I think about concurrency, this is the kind of image that I conjure up. I hope you have all seen this film because I'm about to spoil it if you haven't. It's Avengers Age of Ultron. It came out 3 years ago, come on. You should have seen it, right?
Is that the best you can do?
You had to ask.
This is the best I can do. This is exactly what I wanted. All of you against all of me. How can you possibly hope to stop me?
Like the old man said. Together.
Right. So when you think about that particular scene, what's the first thing that comes into mind? Chaos, unpredictability, lots of things happening at the same time with no control over how they happen, right? Now, there's a state of affairs right now. First task, assume this is time. And this is your thread of execution, right? So task 1 gets executed, its results get passed on to task 2, and then task 3, maybe slightly longer, then task 4, shorter, and then task N, it goes on, right? Okay, so this is how we think about code when we're like that and we're looking at whatever code it is that we're writing. However, what if this is how it worked? You get task 1 there, and then task 2 happens on a separate thread. Okay. And then task 3 is on that one, and then task 4 is there, and then whatever. Now, all of these finish at different times. All of these return at different times. How do you deal with that? Do you sort of hold on to things and wait for something to come up and return, and so on and so forth? This is the problem we have with concurrency. It's non-deterministic. It's things happening in several threads, happening all at the same time, with you not knowing what to do about them. But before we continue, I'd like to sort of throw a quick pop quiz, sorry. Who can tell me the difference between parallelism and concurrency? If something's concurrent, we know what it is generally, but then what's the difference between that thing and something that's parallel? Any takers? Yep.
In parallel, you always get the same answer. In concurrency, if you run it again, you can get different answer.
Okay. Well, that's parallel, you said, yeah? What Kidan said about parallel is that you can get the same value each time. Okay. Well, I can postulate that you can also get that with concurrent. So, I will propose a different answer. Concurrent is dealing with a lot of things at once. Parallel is doing a lot of things at once. There's a subtle difference. The difference here is that when you write your program to be concurrent, it's inherently parallelizable, meaning that you don't care about what returns at each stage because you can handle that. Your program can handle that. Now, what becomes interesting is if you decide to run different parts of that program on separate processes. That is parallel. Yeah? Good difference? Does it? Do you get that? Okay. So, you can never run a parallel program on a single CPU because it doesn't have any more to run it on. But you can run a concurrent program on a single CPU, and in fact on multiple ones. Okay? All right. Not to put too fine a point on it, we will focus on concurrency at this point. But if you want to sort of explore the differences between parallel and concurrent, there is a great talk by Rob Pike. He is a co-creator of the Go language, which is famed for its concurrent prowess. And he sort of goes in on that, but he uses Go, which is quite easy to read, but the concept's the same. So you will, and he uses gophers, which is quite nice too, it's quite cute. All right, anyways, so we will focus on concurrency at this time, because as I said, you can derive parallelism from concurrency. So, why do we need to be concurrent? Well, with the proliferation of a cheap commodity hardware, you can run things on AWS without really worrying about things and so on and so forth. We can distribute our work a lot easier nowadays. But we're writing code on languages that were developed in the 70s and the 80s and so on and so forth, with concepts that were developed at that time. And so what happens is that we sort of think in a single track. But in order to harness the new technology for the problems we're having today, we kind of need this stuff. You can derive some better fault tolerance from concurrent programs. And I will get into that shortly. And of course, obviously, you can exploit your system resources a bit better. So concurrency is not, there are problems with it. Can you read? Can you see this? Cool, great. As we saw in that video, it's non-deterministic, right? You don't know who's attacking who, you don't know who's taking down who and all that. There's so much happening at once. And so for us, at least in my little brain, I need order. Problem is I don't have it. And so it becomes a problem. And because of the way we write our programs, there exists something called the Kaufman conditions. And believe me, there is actually an encyclopedia of parallel computing. It's yay big and it's very expensive. But whatever it is you take from this talk, basically those things are in there. And what it says is that when you write your program without mutual exclusion, i.e. if things depend on other things to actually run, that is a condition that could create a deadlock. All right. So, for example, in our sort of parallel thing, if we needed the result from T2 to compute T4, for example, we have a problem. If T2 is not returning, there's a big issue, which is hold and wait. So basically, if I have a resource, and for example, I was reading a file, and that file was locked or whatever, and if I hold a lock to that file, no one else can read it. So I hold it and wait for something else to come up. I'm still holding this resource. That thing needs something else. It's never coming back. I'm still holding that resource. You have a slow machine, and sometimes something that doesn't respond. You don't preempt when you don't sort of foresee certain things happening as a result of you locking or sharing resources. And eventually we've got circular wait, i.e. I'm waiting for you, you're waiting for me, I'm waiting for you, you're chicken and egg, catch-22, call it whatever you want, but the point is that nothing gets done. Yeah? Right. Live locks is a slight deviation on deadlocks. It basically means that it looks like something's happening, but actually it's not. So as a programmer, as a developer, it's like, oh yeah, it's churning. You feel that there's something happening, but actually that program is in an exceptional state or something. And so it's not returning, but it's still running on something. All right? And of course, there's the shared data problem. I have a value, a variable, and I've stored 2 in it. It's been, manipulated by process 1. Process 2 picks up that variable and adds 1. Now, all of a sudden, I have 3. A is equal to 3. But process 1 assumed that A was equal to 2. And so it does its computation, and if you're lucky, you do catch an error. If you're not, you have a very expensive error. It does happen. Now, Edgar Dijkstra, I hope I pronounced the name right, in 1965, published this thing on semaphores. And what he said was that, well, you could treat shared data as a train track. All right, so you know what a semaphore is? A real-life semaphore is basically just flags that you raise up and down to say one can come through, another can go away, and so on and so forth. You stay because the flag is up, it's being used. And it's very synonymous with mutex locks, which is mutually exclusive locks, just truncated to mutex, which is what it is. It's a bit like the way I used to run stand-up meetings when I was team lead. I had a stress ball, and if you weren't holding that stress ball, you couldn't speak. And so what that stress ball was a lock. Someone holding that ball could speak, and if they spoke a little too long, everyone had to shut up and sit down and wait. And sometimes it was unpleasant because I used to talk a lot. And so, we spent 20 minutes just listening to me when the whole stand-up was supposed to be 20 minutes. And yeah, that was a problem. And so, to solve this problem, as I've sort of put down there are a few things from way back, 65, to deal with this. So it's been a long-running problem. But message passing, it didn't come along as a new thing. It's always been there, except that it's now become a bit more relevant to the way we write code. And message passing using actors. The thing is that you can do message passing with other sort of strategies. You could use messaging systems, queues, all that, right? It's great. But I want to focus on actors because that's what I know. Now, why message passing? Well, that shared state that I was talking about? Well, if I'm passing you a message, if I'm sending a copy of the message that I have to you, then we're not sharing that message. We're not sharing that state. You have your copy, I have my copy. You can do whatever the hell you want with it, and that's great, right? Because it doesn't affect me, okay? And also I can encapsulate the way I process that message in that thing that has received the message. So I can say, okay, well, you want to process it in this way, that's good, that's great for you. It works for your business logic, but I want to work on it this way. And that way we are sort of mutually exclusive to each other, okay? All right, so when I heard actors, that wasn't what I was thinking at all. I hadn't heard it before, I didn't know what actors were, and so on and so forth, but I knew actors, I go to the cinema, But, there we go, okay, cool. Carl Hewitt, I'll go through a few of the sort of proponents of this, but the idea here is that an actor is a fundamental unit of computation that embodies processing messages that it gets, storage if it wants to store those messages, it's not by force, and communication. How does it pass messages to another thing, another entity, another process? Okay. Now. There we go. There, that's it. So, Carl, this is from 1973. So obviously, this problem, it's a long-running thing. And these guys sort of published this a collection of commentaries in which he talks about the actor model, and he sort of goes into the mathematics of it and so on. But having said that, about 5 years later, there was CSP, which is the pi calculus, process calculus, sorry, of the actual communicating sequential processes, which is basically a formalization in mathematics of what actors do, all right, which is communicate with each other. Yeah? So, well, that was Tony Hoare, Sir Tony Hoare. It's not a history class, so let's forget about that for now. But the point is that a lot of work has been historically done on this. And what these guys then said were like, okay, well, there are these axioms. Axioms are basically a proposition, which is regarded as an established truth, okay? So for example, sports build character. That's like an axiom. It's not law, it's not, but it's close enough that we take it as truth. All right, and there are some axioms for actors, so that an actor can create new actors. Yes, it can sort of create a hierarchy tree or whatever. It can send messages. That's important. It can send messages to other actors that it knows of. Okay, so it cannot break out of its scope, or it cannot break out of its domain to send something else. And it designates how its own messages should be handled. If it receives a message, it's responsible for it. Not the one that sent it, not anything else. Okay, so it's this sort of sovereign state that does things with its own messages. Okay? Right, now, going back in time a bit, Erlang, on which Elixir is based, was developed in the Ericsson lab by Joe Armstrong and some Robert Verdon, that's it, 86, sorry, thereabouts. They thought about this quite extensively. And what they did was they thought about it in sort of low-level terms. So that PID, that's a process ID. It could be a function, it could be a group of functions or whatever, but the point is that there's an identifier to this process. All right? And the Erlang sort of VM deals with the threading for you. And so what you do is you just say, spawn this new process on that thread, and start running it. Now, inside of this some function, you can then put in a loop that will receive messages, okay? And basically, this little PID bang hello, that's an atom, by the way. It's for those who are not sort of familiar with Erlang, it's a sort of almost like a variable. But what we're doing is we're sending that atom hello to that process ID. And when that process ID or that process receives that hello, we do something. Okay? If we receive something else, we do something. That there is a pattern match. Okay, and that's generally how Erlang works. It matches patterns to emit values or results. Okay, so that's a bit of Erlang showing you what message passing does at a sort of low level. This is built into the language itself. Now, AKKA borrows a lot from Erlang and OTP, the OTP design. OTP is just your, it's a framework around which it's not new technology or anything. It's just a way that we write code in Erlang to make it more standardized. And yeah, so it borrows a lot of that, but previous to that, there were lots of other languages that sort of did message passing, Ada being one, OCaml another, and there's concurrent ML, I think. But then there is also a CSP, which sort of formalized this into a sort of calculus. But I sort of mentioned that, so I'll just sort of go quickly. So in summary, actors will receive messages through a mailbox or some buffer of some sort, and they will act on those messages as soon as they receive them. They will communicate with other actors by sending messages through a pre-agreed protocol, and they maintain internal states. This is actually important. No other actor can affect another unless it was its parent. And even that, it doesn't do that. There's what we call parental supervision, which I will talk about in a bit. But the last bit is that it will supervise other actors that it creates. So for example, if I created an actor, I can supervise its work. I won't just let it run amok doing stuff. I will sort of keep an eye on the things that it's doing. Okay, so actors in SCALA. Before 2.9, SCALA, there was an actor implementation in the language itself. And I think at that point, Mr. Odersky, Dr. Professor, whatever he is now, I'm not sure, BDFL, Odersky decided that let's take it out because AKKA is doing a good job at it. And AKKA is a library that you can import into your SCALA code, and boom, you have actors. Well, it does provide several things, but these are the main ones I really want to talk about right now. The actor itself is, if you know anything about SCALA, you would know that it's got what we call traits. Traits are a bit like interfaces with implementation code. So it's like behaviors that you can write on top of your classes that they can extend. And an actor is one of them. It's a trait. It's a trait with one thing defined in there, which takes a partial function, and that's the receive method, which you sort of saw a parallel to in the Erlang example. So there is a receive method in the SCALA actor as well. And basically it runs exactly the same way. It's a loop that will run and dispatch things to a separate thread when it receives a message. Okay? There is a system which is basically a domain of control for all actors. The system is actually the thing that creates the actor for you. We'll take a look at some code for that in a bit. And also there is the actor reference. So basically when the system has created the actor, it hands you a reference. It doesn't give you the actor itself. Because remember, the actor only controls its own state. You can only refer to that thing. You cannot have that thing, if you see what I mean. You can send it a message, but you cannot touch it in that sense. Okay? Are we clear so far? Okay, moving on. Great. So, as I've just said, we don't actually create the actor. We call actor off on the system, and that returns a reference for us. And the trait also enforces this receive method that we have to define in whatever actors that we build moving forward. Okay, so these are the four core things. It does more things than this, but these are the four things that, that an AKKA actor would do. It would create another actor if it can, if it must. It will send messages, it will supervise, and it can become. Now this is interesting because then what it is changing its internal state. I don't know if any of you sort of know what a finite state machine is, where you have a machine that can sort of transition between one state at a time and so on and so forth. But that's the point of an actor. An actor will receive messages, it will behave in a certain way until it chooses to then become something else, at which point it behaves differently. But that's the point. The point is that it controls it itself, basically. Yeah? Right. So the system, as I said, is our logical domain. It controls the supervision hierarchy. So in a system, you can have a sort of hierarchy of actors on top of which you have your system itself. And you will find that the system actually is implemented as an actor itself. Yeah? And it also controls things like configuration. So basically our execution strategies. Should we, in Java world, use the fork join in the way that we dispatch things to threads? Should it route, how it should route to messages if you're clustering actors and such, and all that. There's a lot of sort of configuration that we can put into that, including things like how many threads it should even use, right? So I'm talking, waxing lyrical about actors and such, but the problems I'm kind of describing are, can be solved in some cases with our object-oriented model. The things that objects, we've been writing plain objects for a while now, they've been working, why not, right? Well, let's consider an example. Let's say we wanted a log processor. We wanted something that would take log files, it would read log files, and then it would store lines from the log files into a database so that we can do things like search, that thing that Kwabena does for us and all that. Let's just say that we wanted to do this. Using a simplified sort of call stack where we have a runnable log processor, we process the file, we start our DB writer, we write the rows in, we open a connection, and we write rows as we go along. All this looks fine, yes? It makes sense right now, right? Okay, now, this is multi-threaded. You have a lot of them running. It could be the same file, it could be several. We don't care. The point here is that let's say we were doing some connections to the database and all of a sudden MySQL goes away. Wherever it goes, I don't know, it does that sometimes. Now, we have a broken connection exception here. This is going to bubble up the stack. It's going to go up. There's an exception that's going to get thrown to wherever it's going to go. And then all of a sudden, our log processor knows about our database. Okay, well, what does a log processor do with database connections? I wrote the code to process logs, not to fix database connections. All of a sudden, I have an exception about the database. It becomes a problem. Let's take that same thing and lift it and put it into what we have for actors. That's an actor, that's an actor, that's an actor. Okay? Now, this file watcher here is looking at our log file. So it gets the file, it takes out a line, and it passes it on to the log processor. That spreads it out into a nice column thing, and then we send it to the DB writer. Great. Okay, so it's sending messages across. Now, let's say that breaks. What happens? Well, we don't go there. We don't tell our log processor, we tell our supervisor. Our supervisor is the one that looks at what's happening and goes, well, okay, what do? We can restart you, if that's possible, or we'll just kill you and replace you. It happens all the time, Yeah, it's a ruthless world, what can I say? But the point here is that something gets done about this thing, but in the right domain, okay? In the right, where you would expect it to be done, all right? We're good on this so far. Great. Now, this is a breakdown of that exception that you saw, right? So there's a broken DB connection. It goes to the processor. What we do is we create a new instance of it, and we pass the reference down so that it's the reference that we have, all right, which we pass on to whoever is communicating with that actor. Okay? Supervision. We've got a hierarchy, as I said, within the ACTA, the ACTA model. This ACTA model, sorry. There is the user namespace, we can call it that, and then there is something above that, and then there is something above that. So there's a system supervisor, there's the user one, and then all other actors that you create as a developer. All right, now that falls under the user one. Not to go into too much detail on that, the point I'm trying to make here is that as a supervisor, I can kill an actor. And the way I do that is not by going, you destroy. No, I actually send it a message. I send it a message called the poison pill, which is quite, creative. I think someone was bored, had a few beers, and they decided, yeah, let's call it poison pill. Yeah, so take this pill, you'll feel better in the morning kind of thing, and you take the pill and then you basically just die. And the poison pill will only be reacted to if that message came from something that was supervising me. Okay, so if I got a poison pill from someone on a horizontal sort of level, I would not react to that. Okay? Makes sense? So even with killing and restarting actors, that is controlled by the actor itself. Okay, so we don't violate these axioms that we've just talked about. Okay? Okay, so moving on to some supervision strategies. 1 for 1 basically just means one actor dies, we replace it with another one. That's it. All for 1 means that that actor that just died was so critical to our entire system running that when it dies, we have to bring everything down and bring everything back up. Yeah? Something like maybe a session. Something that an actor which was handling a session, for example, was dealing with. All other actors were running on behalf of this session, and that actor died. Well, that session is no longer valid because when it comes back up, it will come back with new data. Everything else becomes invalid, so everything has to go down and come back up. Does this make sense? Cool. So, enough talk. How about some code? If I can get out of this and bring out my trusty IntelliJ here. I'm not going to show too much here, but just this is a simple, yeah, I think this works. Can you all see this? Okay. I'm going to sort of just go through all these actors, and then I'll run it, and then you'll see what happens, all right? Game of Thrones fans. Yeah, I've had a few, that's enough. One would have been enough, that's fine. All right, so we've got a class here, which extends. In SCALA, you don't do implements because it's already implemented. You extend the trait, all right? With just means that if any of you sort of are familiar with mixins, it's a bit like that. We're mixing in the login trait here as well. And what we're saying is, well, we're defining an actor, all right? And of course, this here, as you can see, it's overriding something, which is from the actor trait. All right, and it's defined receive. Now, if I actually go into this thing that it's overriding, you will see that it takes a partial function. Yes, go there. That's the point. Brilliant. How do you get out of this thing? Exit. Yeah. Okay. Cool. Oof. Tiny. But if we click into that, yes, brilliant. Okay, so let me just go to, this is from the AKKA library, by the way, so I didn't make this up. It's actually, yeah. So this here, def receive, sorry, I don't know if can you see this? Can you, okay, good. So def receive here needs an implementation, and that's what we implement when we extend this thing. And basically it returns, that's the return type. And if you see what I'm hovering over, it says that it takes a partial function of with an any parameter, so anything. reference the SCALA type system. It's arcane, it's crazy, but it works. It's any, it will take anything and returns a unit, which in Java terms means void, or it means nothing. All right, but it does return something, it's called unit. All right. Never mind that for now. But that is what the receive thing does. And basically, once I've defined that thing, this here in the curly braces here is our partial function. Okay, we could take this out and execute it somewhere. If we had the context, it will work. That's the point. Okay, so as Matt was talking about value classes and so on and so forth, that's generally how this stuff works. This is a value class called greeting, which takes in a string of whatever message it is. So we can match, we can pattern match. As you saw from the Erlang code, it's basically been stolen here. And basically what we're doing is we're matching on that greeting case class, as SCALA calls it. And when we match on this, what happens? Well, we log something out. We log ourselves, our name out, and we say that we got a message from the sender. The sender there, where did it come from? Well, SCALA has something called implicits. It will take 2 hours just to cover what implicits do in SCALA. And to be honest, I know a little bit of it, but I'm not, yeah. But the point is that that is implicitly defined in the actor trait. Okay, and so we can basically get the name or the reference of that sender, the person who I got the message from, so that if I needed to respond, I would use that reference and I'll send it a message too. Which is exactly what I'm doing here. So I take the sender, bang, as in Erlang. I send it a case class with Hodor written there because that's all he says, right? We all know this. But then I've put in a little thing here because I'm sleeping the thread, all right? I've put that in to illustrate something so that when I run it, you will see what I'm talking about. Okay, if I get anything else, I don't match anything, I just print that out, okay? Now we're printing out. It's side effecting, but never mind that for now. That's too much detail. Now, Aya, one of my favorite characters in the whole thing. She's also an actor here, and once again, she gets a message, and she says it back to you, basically. Okay? Yeah, and if she gets something else, she says winter is coming, rather ominously. And then there's a grumpy imp, all right, who then sort of gets a message and says something, says go away or something like that because he hasn't had enough wine or whatever. And when he gets something else, he sends something. Yeah, whatever. Okay, now this is basically my runnable. Okay, the app in here, I'm extending that trait, and what it will do is it will collect everything into a main. Okay, it's a bit like saying in Java doing public function main with arguments, string, array, and that sort of thing. It does all of that, but that's just shorthand. Okay, I could have easily taken the extends app out and actually defined my main method in there if I wanted to, but this makes it easy. Now, in here, what I'm doing is I'm defining my system first, okay? And then I say, well, Hodor here is an actor of that system that I've just defined, and its name is Hodor, but use the properties of the class that I defined up there, and that is how I respawn. I can respawn other actors to replace it, because if Hodor died, if Hodor died, the system could then create another Hodor with properties of that class Hodor. And it will be exactly the same thing. Perhaps a different memory space, but the same thing nonetheless. Okay? And the same for Aya and the same for Tyrion, Grumpy Imp. So far we're good, right? All right, now let's get them starting to talk to each other. We send hello to Hodor. Notice that hello is just being sent out of the blue, okay? There is no sender. We're just sending a message. Then we use that API there, which is tell. Tell basically allows me to specify who the message is coming from. Okay, so it says, tell Hodor good morning, and that message is coming from Aya. Okay? And you can see a pattern here. And you can see a poison pill. Yeah? And our system terminate. Now, moment of truth. Shall we run this and see if we have any errors? We probably will, but that's the point of live code demos, isn't it? The stars have to align for everything to work. Okay, so if I run that, let me see if I can blow this up. Brilliant. Can you all see this? Great. Let's do that. Right. So I sent a message first, and it got a message, and Hodor said Hodor, as he usually says. He prints it out. The login messages you will see as logs like this, but the print ones will not have that. Okay. So you can sort of follow me. Now, if you notice, the astute among you will notice that these are not in the order that we sent them. Okay? Some of them, especially the one that says dead letters. We sent Hodor a message, but Hodor was sleeping for 2 seconds. And then the system terminated. Okay? And so what we have there is that it received a greeting, but it didn't know who it came from because the system was dead. It didn't know who it was going to because the system was dead, along with Hodor, who was supposed to be receiving that message. And so dead letters there is basically a mailbox, the default mailbox, where if there is no actor to receive, it goes into. You can then go in and debug your dead letters and see what happens. But then that's what that is. Okay, so we've got an interleaved sequence of occurrences here. All right, now you will have to forgive me because this was sort of extracted out of a much longer lecture. It was a 3-hour lecture that I've sort of compressed into however long I've been talking for. And so I think that this sort of gives you an introduction to what we're talking about when we say we're concurrently programming with actors. It's not sequential. We interleave our results, and sometimes we have to be prepared to be able to handle things like these. Okay? And that's the idea. All right. So, as usual, I would like to sort of wrap up with the words of Gene Amdahl. He used to work at IBM. He's famed for being like the, godfather of parallelism or whatever. And what he says is that in order to achieve speed up, we can employ parallel processes or exploit parallelism either by changing our algorithm, our code, from sequential to parallel, or changing our approach. Now, concurrency here is not a silver bullet. It won't work for every situation. There are certain times when you will have to have a transaction, where you will have to have things happen in a sequence, at which point that is not the solution for you. But what he's saying is that if you want to achieve speed up, you have to look into your code at the points where you can execute off-site, as it were. And if you can do that, for example, if you take the classic example of the Gregory Leibniz series for calculating pi, for example, typical example of something you can parallelize, because it's just fractions that you're subtracting and adding alternatively. Addition is associative. You don't care in which order you get it. You get the different sides, left hand, right hand. You don't care. All you care about is that you've got the values. And when you sum them together, it always adds up to whatever it adds up to, regardless of which order you put them in. That is a problem you can't solve with concurrency. But certain things, like withdrawing money out of your bank account, it kind of has to be a transaction, doesn't it? Because then you have problems if something doesn't check out. For example, if you don't have enough funds, or that thing that's supposed to check, if you've got enough funds before it even gives you the money, doesn't return, or returns later than you actually withdraw the money. So you end up with £2,000 when you had £0 in your account. Things like that you probably want to do in sequence. So the problem sort of, defines what the solution should be. And I think in a nutshell, that's what that is about. So, any questions?
Actually, I would like to ask a question for the actors.
Yes.
So you said for each actor there is a supervisor. What about the supervisor?
The supervisor has a supervisor. Even so as I said, there were like, there's a user space, there's a system space. There is actually an actor that lives out of the system called the one that walks among the bubbles. That's a Doctor Who reference in case you didn't sort of catch it. But it is there. It's a sort of virtual pseudo super actor that sort of lives outside of this thing that supervises that. If a message gets to that, you're in big trouble. That's the point. Because as soon as it gets an exception, as soon as it gets something, an inkling of something going wrong, it will kill everything going down, which includes your supervisors and everything. Yeah.
I've got one more. After. So let's say that two actors hold their messages, right?
Yep.
And one actor depends on the other. So,
okay.
Is that the case?
I suppose it depends on what your problem is. To be honest, I wouldn't see why an actor should depend on another, because it runs independently of that. It responds to messages it receives from that one, but it doesn't depend on those messages to live or to run, to function properly. It's just there waiting for a message. It gets a message, it executes, and it moves on. If it doesn't get a message, it just sits there bored. Yeah. Any other questions? There's one other.
Hi, just wondering, practically speaking, how performant is the system, in terms of runtime compared to, say, handcrafted synchronization locks? Or I think that's the one thing that I'll be concerned about, and also load as well. So there's performance side and how it can take on.
His question was about performance and synchronizing and so on and so forth. Well, the idea of message passing is that you don't have to synchronize. The idea of passing messages across several actors is that you don't have to think about orchestrating those messages. Now, you do raise an interesting point in terms of memory consumption and resources and stuff. But actors consume such a small footprint that you could fit something along the lines of 2 million in like a gig of memory or something like that. I forget the numbers, but it's there. And they're quite lightweight. Now, if you were going to run this, I'll give you a typical example. There is a library called Streams in AKKA, which basically does, infinite stream processing and things like that. Now, whenever you pass a message down from a stream to some other stage, an actor handles that on a separate thread until that comes back. And those things are really quick. So in my sort of practice, I've not come across a situation where an actor has been responsible for a bottleneck if it was written properly. Yeah, because the very concept of programming with those constructs mean that you eliminate the need to think about your threads, the need to synchronize, the need to rejoin, the need to fork, and so on and so forth. Because after all, Java util concurrent does that all for you, right? And that's what the actors sit on. Yeah. Cool, brilliant. Well, thank you guys for your attention. I know I've been quite verbose, but thank you and have a good evening.